Today we are treating electrodynamics, electromagnetism and optics. And these are the synopses that we are going to cover under this course as an introduction. So we'll start with basic derivations of Maxwell equations, which will give us the preliminary or the preview of this course. As you can see here, the first one starts with Lorentz force. What is the Lorentz force? Lorentz force is the total force of electric and magnetic fields when a charged particle is moving in a conductor. I told you earlier that Lorentz force F is what? Force due to electric plus force due to magnetic field. And force due to electric field, everybody knows, is Q and E. E is the electric potential, Q is the charge, and this is the electric force with an arrow here. Mind you, remember, electric field strength is known as force per unit charge. So when you cross multiply, you are going to get what? Force as E multiplied by Q, which is electric force. And magnetic force is given by QV cross of B, where Q is the charge, V is the velocity of the particle, and B is the magnetic field. So if I add my total Lorentz force, I will have what? QE plus QV cross of B. I have Q here and Q here, so I will factor Q outside. So I will have E plus V cross B. And this gives me my Lorentz force. But this course is treating what is known as field theory. In field theory, we are talking about force density. That means we are talking about force per unit volume. So this Lorentz force is not going to stand. So if we are taking force as Lorentz force, which is force per unit volume, all these things here will be what? All over B. Whereby we have E plus V cross of B. I hope it's clear. This Q over V is nothing but charge per unit volume. Because Q is charge, V is volume. And charge per unit volume is nothing but charge density. I hope it's clear. And charge density is represented by this symbol rho. So therefore, this equation, Lorentz force turns into what? Rho into bracket E plus V cross of B. Now, if I expand this bracket by opening it, I will have plus this one here multiplied by velocity cross of B. Isn't it? There is what we call current density. Current density is given by J, which is given by the volume multiplied by this charge density. And current density is also a vector J. So now our Lorentz force turns into F is equal to rho E plus current density coil of what? B. So this is the total force acting in an electromagnetic particle in a static or pseudostatic medium. Now let's go into flux. What is a flux? If you have this one here like this, if water is gushing out of it, this surface here is a sphere, isn't it? If you have a surface here like this with water gushing out, this water is a field because it is moving with a velocity. We can say force, we can say velocity. So the integral surface of this field, vector field, around this closed surface is nothing but flux. Literally, flux is just flow. I hope it's clear. So if something is flowing outward or inward through any surface, we call it flux. So flux of this water flowing into the pipe here is the integral of this vector field, which is velocity, multiplied by the surface, v dot ds, if this is velocity. If it is a force, we say flux due to a force is the integral of the vector field of that force, isn't it? With the surface. Mind you, this surface, the force is moving perpendicular outward to the surface radially. We treated this thing in introduction to electricity and magnetism. There is what we call electric flux. If this happens to be a point charge inside this sphere, the point charge which is positive radiates outwards. You know that? If I have a point charge Q, which is positive, The lines of forces are moving what? Outwards. So therefore, electric flux is nothing but the integral of this force field, E dot ds. And these are all over the surface of this sphere, or the shape it is enclosing. And the surface must be closed. Isn't it? Now, if the current is flowing, we have what is known as flux due to the current, which will have our current density over the surface. This is J, current density. There is one thing I want to bring to your own notice here. When flux is flowing outwards, this becomes the source if it is Q positive. And when it is flowing inward, it becomes a sink. If when it flows water down here, this is the source. And when it goes into the sink, it becomes what? A sink. But in any hollow surface, in any closed surface, if flux is not going in, if flux is not going out, that means this surface encloses no flux. And that is what happens in the case of magnetic field. And I told you that magnetic monopole does not exist. If you find a magnet which has north and south pole enclosed in the circle, the north pole goes out and it comes into the south pole. I hope it's clear. So this becomes zero when you are considering the flux because it is a magnetic field. There is no magnetic monopole that will give source out. Neither is there south pole that will bring the source in. The lines of forces in a magnet cancel each other, and that is why the flux in a magnet, when it encloses any surface, is zero. And you cannot break this cycle, because when you break this cycle, you have defied the rules. Isn't it? So we are going into what? Gauss's divergence theory and Stokes theory. See what Gauss did. Gauss provided an alternative method of finding the integral of a volume instead of a surface. Because your fields are not only passing through a surface. You have 3D, X, Y, Z. I hope it's clear. So if field is passing through a surface that is in a form of a volume, we are not considering flux. We are now considering divergence. That is what he did. He just applied divergence theory to all these ones and he changed them to volume integral. I hope it's clear. So now, let me just give you what this Gauss says. If there is any question, I'll welcome it before we proceed. I hope it's clear.
Yes, sir.
Because we have so many things to cover. So it's better for us to go at our own pace. I know you know the symbol of divergence, D, which is a nabla. If you put dot here and it's at any vector, we say it is divergence of this vector field. Isn't it?
Yes.
Divergence is nothing but nabla, which is what? I d over the x plus what? J d over the y plus what? K d over the z. How many dimensions is that one? So volume is in how many dimensions? So divergence theory is nothing but application of this one here. Isn't it? You have your flux of electric field, which is what? Integral of E dot S, and if you apply it here over the volume area, you have your dV. This is the divergence theory. So when you have a divergence of electric field, it is the same thing with the flux, and this is the surface. So if you are changing from surface to volume, you are applying divergence theory. If you want to go back to surface, you apply the flux. We consider also for the magnetic field. If the flux due to a magnetic field is B dot S, apply the divergence, we have what? Divergence of B, isn't it? Over the volume, all enclosed by the volume. That is all what divergence is. Is it clear?
Yes.
Okay. So now we are going into Stokes' point theory. For Stokes, what he did, he applied line integral instead of volume. Somebody did for volume, we have surface, and we are now going into what? Line integral. So now, let's see on this side. All these things are preview. I think we have done them under Introduction to Electromagnetism. If you have L, you have force dot L is equal to the integral of coil of the force over what? The surface. So Stokes is telling you that the coil or rotation of the force this is a force in a field, isn't it, with a surface integral, can be converted to a line integral with line L here, which will give you F dot dl. That is just the basic idea Stokes introduced here. I hope it's clear. The Gauss's divergence theory and the Stokes theory will be used in driving the Maxwell equations, and it will form the backbone of electromagnetic potentials. And we go into waves and the rest. So now we go into Gauss's law. Please, Maxwell's equations are 4. You know that. But the changes in the medium. If the medium is static, isn't it? A static medium with respect to the coordinate axis x, y, z, we call them Maxwell equations. But if the medium is pseudostatic, is false, pseudo. For the pseudostatic medium, we are not considering Maxwell equations. We call them Gauss's first law, Gauss's second law, Ampere's law, and Faraday's law. I think that is listed here. This is Gauss's first law and second law, Ampere's current law, and Faraday's law. These 4 of them are known as Maxwell equations when the static medium is in respect of x, y, z. But if it is pseudostatic, is not real, we call them these equations. So now, let us start with Gauss's first law. Most of these things are trivial, I told you. Find the flux around an enclosed surface. The flux, I told you flux, psi is just flow, isn't it? The flux enclosing any surface, he said, is given by charge enclosed all over the permittivity. That is what he said. If there is a surface like this, and water is gushing out like this, isn't it? I hope it's clear. And this water is a vector field, then it's a force or velocity. If this is a vector field of the water, the flux enclosing this sphere, water is flowing out here. The total flux is the charge enclosed over permittivity of free space. How did you get this? 211 watts. We said electric field multiplied by ds, isn't it, is known as flux over the enclosed volume. But you know that electric field is kq all over 4 pi epsilon naught r squared, isn't it? And you are multiplying by ds, and you have your integral. The surface area of a sphere is nothing but 4 pi r squared, isn't it? If it cancels out, you'll be left with what? You'll be left with kq all over what? Epsilon naught. And if q is outside the integral, you have what? Q all over epsilon naught. Isn't it? I hope it's clear. The integral will go with the s. Integral will go with the s. So that your flux is nothing but charge enclosed all over what? Permittivity of free space. So this is known as Gauss's first law. But the major thing here is for you to know how to write Gauss's first law in integral form and in point or differential form. So let us go into Gauss's law in integral form. Isn't it? Over permittivity. I need questions now from you so that we proceed. Any question?
No question.
You're supposed to have questions now so that I will know that something is happening. Huh? What we call discrete charge distribution. Discrete charge distribution. In any kind of a surface, we have charges that are discrete. So what happens here is that if they are discrete, they are elemental. all over the volume gives you charge density. Charge over volume is charge density. So if I want to get my total charge enclosed in any sphere, it's nothing but this one, the integral. Isn't it?
Yes.
And you know that Gauss's law says psi is equal to what? Charge enclosed all over what? Permittivity of free space. And it's nothing but, if you replace this charge with this, what are you going to get? Integral of P dV all over epsilon naught. Isn't it? So flux is nothing but E ds, which is equal to dV over epsilon naught. I hope we are clear. But see what is happening. This is surface, this is volume. Isn't it? I hope it's clear. So now, this is known as Gauss's first law in integral form. I hope it's clear. Isn't it? Gauss's first law in integral form. Now, what to do to get the differential form is to transform this one so that it will also be in volume. And nothing is done by just applying the divergence theory. I told you what the divergence said. It converts surface to vector. That is why there is this del, which is in x, y, z. So when I introduce divergence theory here, I am converting this thing to what? Volume integral. And when it gets converted to volume integral, we find our differential form. How do we do it? This one is the same thing as what? Divergence of what? E dV into what? V. You remember? And it's the same thing with what? V dV over epsilon naught. So if you have V here, you have V as the integral, they will cancel out. So you have is equal to all over permittivity of free space. This is the Gauss's law in point form or differential form. Because you must be asked to drive either the integral form or the differential form. Isn't it?
Yes.
So now see something here. When you multiply this E naught by E multiplied by E naught is known as flux density. Please. The density, the way this flux is moving out, that is it. And it's given by a symbol which is known as D. So I can say divergence of D is equal to charge density. Please, this is also acceptable as the Gauss's first law in differential form or point form. This one is more acceptable compared to this. If you write this one for me in the exams, I will give you more marks. Isn't it? This one here. This one here. Because you have expressing it in terms of flux density. Is it clear? The next thing, in linear isotropic medium, if this place is having the same surface area, the same characteristics, I hope it's clear, that is linear. And towards all directions, it maintains the same homogeneity. This E naught changes to what? E. Naught changes to E. So that D is equal to E with this one here. So that is what is happening. So calculate on some computations, they will ask you linear isotropic medium, and if you use permittivity of free space, you fail. And this is known as permittivity of the medium, because the medium must also have its own permittivity, isn't it? So now we go into Ampere's current law. Okay, second Gauss's law, please. Second Gauss's law is nothing but, say here, it says if you have a magnet, isn't it? The magnetic flux radiating around a closed surface is zero. That is what Gauss's law says. That means if I have a flux due to a magnetic field, this surface, V dot ds, I will have zero. And it's true. I told you magnetic monopole does not exist. What goes out comes in. So there's no flux to calculate. Nothing is moving out. That's one of the questions that is still in advanced physics if you can solve it. Do we still have magnetic monopole? Can you divide this magnet to the extent that it's only one side that is pushing something, the other side is not receiving? So now, please, this is Gauss's divergence, Gauss's law, please, in integral form. I will change it again to differential form because they always ask this one. How do you change it to differential form? Point form. Apply divergence theory. I don't want it in surface. I want it in what? Volume. So what will I do? Divergence. So my divergence is divergence of B round this surface here. It gives me 0. So this is equal to B dot S. So please see what happens. This one is going with this, so that I will have my divergence of B is equal to 0. So this is the point form or differential form of Gauss's second law. Can be asked. I told you, first question must be all these things. Derive the differential or point form. Isn't it? You have 1 or 2 proofs. And if we have a question, we can add there. So we go into Ampere's current law. Isn't it? Aha. Any question? If you have a question, please ask you. What is the where is the beginning of what? Gauss's second law?
Yes.
Okay. I told you here, if I have a round surface and a magnet enclosed in it, the total charge crossing through it is 0 because a magnet cannot be enclosed in this surface except you break the surface. Isn't it?
Yes.
So the flux, there is no flux there because the flux is 0. Isn't it?
Yes.
Let's go into Ampere's law. The third Maxwell's equation. Isn't it?
Yes.
Aha. So what did Ampere says? Before we can drive this Ampere's law, we have to know what is known as charge continuity equation or charge conservation law. Isn't it?
Yes, sir.
Aha. Now, if you have an enclosed surface, charge continuity equation or charge conservation law. If you have an enclosed surface, if you have a point charge, let's say positive point charge, positive.